PNP. So if same signal is applied to both the base of two transistors, one is going to be NPN, another is going to be PNP. The actions are different. The actions are opposite because each transistor will react to the base voltage differently. NPN will accept happily the positive half cycle signal which is given to the base, but PNP will reject it because the emitter base junction will be reverse biased. So the reverse case will be during the negative half cycle where your NPN will never work, and because it is reverse bias, and PNP will work because it is going to be forward bias. So for having good performance, ensure that both NPN and PNP transistors are made up of the same material and same technology and have ideal parameter. That's why you use the name symmetry. Complementary indicates opposite families, NPN and PNP, but symmetry indicates same set of parameters for PNP and NPN. How do you get same set of parameters? You have to have the transistor should be made from the same material, same technology, and should have the same parameters of the device. So when you ensure that, you can expect a very good performance from this complementary symmetry class B push-pull amplifier. So in addition to reduce the cost and weight, elimination of transformers will enable this circuit to be used for high frequency also. So we didn't use transformer anywhere, but if you see class B push-pull amplifier, the initial circuit, you have one transformer at the input, you have one transformer at the output, but we have eliminated two transformers. So when you eliminate transformer, the circuit will obviously become very, very small. It will be very, very handy. So the cost will come down, the weight will come down, it will be looking very, very slim. So that is one more advantage of complementary symmetry push-pull class B amplifiers. So same way here also, the efficiency is 78.5 as we derived for class B push-pull amplifier. The output power is half VC square by RL, average power, so half VC square by RL, and the maximum value of signal is limited by the VCC. So you can write RL equal to VM by IM, IM is equal to VM by RL. You know VM maximum voltage is going to be your VCC, and you know the DC power is 2 by pi into VC into IM. See this VC by pi into 2 IM actually. Since I'm using two transistors, I'll have two collector currents. So 2 IM is coming, and VCC by pi is the average value. And IM, you know, it is VCC by RL. So 2 by pi VC square by RL. So divide both efficiency equal to PDC by PAC. If you divide, you get pi by 4. And substitute for pi as 3.14. If you substitute, you get the efficiency as 78.5%. So this is the efficiency of complementary symmetry push-pull amplifier. This efficiency is going to be same as that of your conventional class B push-pull amplifier also. So these two amplifiers are going to have the same efficiency value, 78.5%. I again repeat, the efficiency is very high because each transistor is on only for 50% of the time. So when you don't use the transistor for the remaining 50%, there is no current flow, there is no power loss. In that case, you're going to have an savings in the power and your efficiency is going to increase. But at the same time, this device is going to be a highly non-linear device. I told you in the very beginning, efficiency and non-linearity are proportional. If efficiency is very less, non-linearity is also very less. If efficiency is very high, non-linearity will also be very high. So class A has an efficiency of 25% for normal coupling and 50% for transformer coupling. So the efficiency is also going to be relatively, efficiency is less, non-linearity is also less. But class B efficiency is 78.5%. It is going to be very, very high. The non-linearity is also going to be very, very